on this episode of Science. Hi, welcome to the show. My name's Nate Macon. I'm the Skyview High School physics teacher. Today, we have a wonderful show about circular motion. But before we get to that, let's give a big shout out to Skyview House DJ Chaddles! Okay, so circular motion might sound a little bit technical, but let's put it in context. When a race car goes whipping around the track, why doesn't it go flying off into the stands more often? Why do satellites maintain their orbit around the Earth? And what keeps the needle in the groove on a record? Because we're going to find out. To do that, we're going to look at concepts like acceleration and velocity. So this is the part of the show where I normally launch into some awesome experiment using my physics team. But honestly, my students have been really needy lately, and I just don't know if I have it in me. So I'm going to see if I can do this one without them. And there's one behind me, isn't there?
Hi, Mr. Macon. We need help with one of these homework problems. We don't get it. And, for future reference, if you want to hide from your students, the middle of your classroom's not the best place to do it.
What are you wearing?
A clean suit.
Yeah, but why?
Because it's disgusting in this classroom. You have stuff everywhere. You have a sandwich behind your printer. Why? Why do you have a sandwich behind your printer?
Yeah, I was saving that for later.
It's been here for at least 2 weeks.
Yeah, I meant later.
Right. Can you help us with problem 42? It's the one about the gravitron, and we really can't understand why the sum of all forces is not zero.
Yeah, I think I can help you, but I'm going to need my ham sandwich.
I'll get it.
Thanks, but you're going to need to hold on to that. So let's take a step back. Kendall, you wanted to know about the sum of all forces and why it's not zero. Remember, a force is just a push or a pull, okay? And it causes things to change their states of motion. And what does that mean? That means if you have an object that is standing still or as still as at rest, it's not moving, and you provide a force, that object's going to accelerate. It's going to change its state of motion. Well, things we put on turntables also accelerate. They also move. All right? They change the direction that they're going, and therefore we have to have a force. Anything that moves in a circle has to have a force applied. All right? So think about it. Have you ever seen something spontaneously move in a circle? Ever? Okay. I'm going to need that sandwich. So to truly understand circular motion, we have to understand forces. Like if I were to take this sandwich and throw it.
Like towards the trash can?
No. Why would I throw away a perfectly good sandwich? Anyway, if I were to throw this sandwich, would you expect it to just move in a circle?
No. But it might get up and walk away.
That's right. It can't move in a circle unless we provide a force.
Okay, but I still don't understand why the sum of all forces isn't zero.
Okay, let's start at the beginning with a couple definitions. And you're probably going to hear a couple of words that you hear a lot in sports. First, let's talk about velocity, which is the combination of direction and speed. An object with velocity is moving towards something, like a fastball moving towards home plate. Pretty straightforward stuff. So let's switch from baseball to basketball. If I were to roll this ball across the floor, it would have speed in a specific direction, right?
Yes.
So if I wanted to change its direction, I would also have to provide a force, meaning I would have to use my foot or a broom or a stiff breeze to cause it to change its direction of motion.
Sure, because velocity is speed plus direction, right?
And if it changes velocity, that means it accelerates, right?
Absolutely. And this is where the sports terms and the science terms really aren't the same. Sportscasters say that someone accelerates when an athlete is running fast. But in physics, acceleration means that an object is changing velocity, which we defined a moment ago. Okay guys, let's take a physics squat. So if I give this ball a push, it's going to change its state of motion, right?
Oh yeah.
Just like this. So if I provide a force, an object's going to change its state of motion. Well, if I provide a force to a moving object, like the basketball, I can change its direction.
So velocity is speed plus direction. But if you change the direction, then that's still an acceleration.
Right! And that is a good physics squat. So now that brings us to circles. And what I've done here is I've tied a string around my sandwich. And at the risk of ruining it...
Wait, you can ruin it more?
What?
No, nothing?
Oh. Okay. Well, at the risk of ruining it, I've tied it with this string. And what I can do is I can cause my sandwich. Right now, it has one force on it, force of gravity, and another force of me holding the string. And what I can do is I can cause it to change its state of motion, change more specifically its direction of motion at every point around a circle. And so I have to get it swinging. And so if I swing it, realize it's accelerating. It's changing its direction. And a change in direction is an acceleration, as we just talked about. And so therefore, the sum of all forces can't be zero. And that is the answer to your homework question.
Hey, cool. Can I try that?
Sure. What? Hey, that's my sandwich.
It's gone, Macon, gone.
That was a perfectly good sandwich.
No, it wasn't. It already smells better in here. I can't believe you're gonna eat that.
I can't believe you didn't want any of it. Well, you having no regard for my dinner still proves my point. Let's go to the slow-mo. So my physics team would like to give you another example of circular motion, or centripetal motion. I am going to go mourn the loss of my sandwich. DJ Chaddles, drop the beat.
So today we are going to talk about the kinds of forces that can be the centripetal force.
Now, as that nickel moves in a circle, at every possible moment, there is a force being applied to it in order to keep it moving in that circle. In this case, the force acting between the turntable and the nickel is friction.
If we increase the speed of the record player, then we increase the amount of force that we need to keep it in a circle.
Let's take a look at the motion of the coin a little bit more closely. Notice how the coin is moving in a circle. And that means there must be a force there to keep it moving in the circle. And as my student said, that has to be friction in this case. But notice, at position 1, position 2, and position 3, the direction the coin would move, if it could move in a straight line, is different. At position 1, it's going one direction. At position 2, it's going a second direction. And at position 3, it is going a third direction. Notice it's changed directions at every point. Now, while the coin has not changed its speed, the direction change also counts as a velocity change, because a velocity has both a direction and a size. And so since that size hasn't changed and the direction has, that means we still get an acceleration, and that means we still get a force. The direction of that force has to be pointed towards the center of the circle. Now this may seem confusing, like if you were going around and around and around on a merry-go-round, your body feels as if it's being pulled outward. But if you're hanging onto the bars of the merry-go-round, or maybe your back is against the bars are actually pushing you back into the circle. Well, for the coin, it's very, very similar. The coin feels as if it wants to move in a straight line, but the frictional force is keeping it in the circle.
Now let's see what happens when we speed up the turntable.
Now, as we speed up the turntable, the amount of force needed to keep the nickel moving in a circle increases, and it becomes greater than the amount of force that friction provides. So, therefore, the nickel just flies off the turntable.
And there it is. Where's Macon?
I'm gonna drop the beat about science, y'all. Bringing that action. But I need a little bit more on the monitor. More on the monitor. All right, here we go. When I pop a physics squad. That's the physics squad, y'all. So what'd you guys think? Good? Yeah? You like it?
Do our grades depend on it?
Yes, your grade is dependent upon it.
Then it was great.
I thought it was pretty good. Here's today's famous scientist.
Today's famous scientist is Johann Kepler. Known best for figuring out how planets revolve around the sun, Kepler was a study in contradictions. 1 foot in medieval times and 1 foot in the modern era. Kepler was born in Germany in 1571 and devoted himself to astronomy as a boy. At the time, just about everybody followed Ptolemy, whose outlook about the universe was kind of like a typical teenager's.
Everything totally revolves around me.
But Kepler agreed with Copernicus, who said that the center of the galaxy was the sun, not the earth.
Whatever.
He published the first ever Defense of Copernicus, and later in life took it even further with his 3 laws of planetary motion. The first law broke from the Copernican model, which stated that the planets revolve in perfect circles. Kepler figured out that the orbits were actually ovals, and that the sun isn't in the exact middle. He did it all without the aid of high-powered telescopes and space exploration. And to make it even more impressive, think about what else was going on in the world at the same time. Shakespeare was writing his plays.
To be or not to be?
The King James Bible came out, and people called the Pilgrims landed at a place called Plymouth Rock. In his 40s, he turned into a lawyer to defend his mother against charges of witchcraft.
I'll get you, my pretty.
Like a medieval Perry Mason, he got his clients off the hook, or, in this case, the burning stake. As modern as his research was for astronomy, he was also a major force in the ancient art of astrology, forever enabling pickup artists everywhere.
Hey baby, what's your sign?
That's right, in the highly scientific field of horoscopes, Kepler was famous for predicting the future. But even with all his astrological skill, it seems impossible that Johann Kepler could ever have foreseen the impact he would have on centuries to come.
So, lots of things move in circles, like conversations with your estranged Uncle Frank. But knowing about circles can be really important. We can chart the motion of the planets. We can launch satellites into space. We can understand how gears on a bicycle work. And that, my friends, is the point. So it's time to check out the old mailbag. This letter comes from Mark. Mark asks, Mr. Macon, in the last episode during Tech Day, you had students complete a task, or try to complete a task. What went wrong? Well, Mark, here's the deal. I think I screwed up. I think when I was engineering the ramp, it wasn't that good. I frankly think that I made the angle way too high, and I didn't really measure out the length of the rails well enough to make sure that all of the kinds of different pieces that we brought from home would actually work. I knew what I would do to make it work, but it turns out that's not what everybody else did, and so it didn't really work. And so the point is, like, hopefully we learn from that. I know I did. And that's the idea. If you want to get your question on air, email us at scienceshow@vansd.org. Well, looks like we're about out of time. Hope you enjoyed the show. I had a sandwich, one of my hidden sandwiches during the Famous Scientist segment, and thought it had lettuce on it. Turns out that was bologna. Not feeling so good. Anyway, until next time, I'm gonna go to the faculty restroom.